So in this video we're going to go over verifying identities that have ratios of trigonometric functions. So we're going to have identities that have numerators and denominators to them. The game is going to be the same as it was in the previous video. You're going to look at the two sides of the identity and you're going to select the side that looks the nastiest, and you're going to transcribe that and then manipulate that side using the fundamental identities until you get it to match the other side of the equation, or identity actually. So clearly the left hand side looks the worst, so I'm going to start by transcribing it. Cosine theta, cotangent theta, or x I guess, plus cosine of x all over cotangent of x plus cotangent squared of x. And the thing that I want to notice when I'm looking at this is that I have a cosine showing up in both terms in the numerator, and if I factor that off I'm going to get a cotangent plus 1, and down here a cotangent shows up in both terms, and if I factor off a cotangent I'll get a cotangent plus 1. So I'll get something that can simplify or reduce to 1 just by starting off with factoring. So first step is just going to be factor a cosine in the numerator, which will leave behind a cotangent, plus, and then a 1. And then you can always verify using distribution that what you have written here is the same as what you had previously. And then I'm going to factor in the denominator a cotangent off each of them. So cotangent x times 1 plus cotangent by factoring. And then I want to recognize that addition is commutative, so cotangent plus 1 is really the same as 1 plus cotangent, so this divided by this equals 1, as long as we don't have a division by 0. So we get cosine of x over cotangent, but the cotangent can be rewritten. Cotangent is the same as cosine of x over sine of x. And I know that division of ratios is the same as multiplication by reciprocals. So cosine divided by cosine over sine is the same as cosine times sine over cosine. I take the thing in the denominator of this complex fraction and I multiply by its reciprocal. And here I see that cosine divided by cosine is 1, and 1 times sine is sine x. And of course, it's only equal to 1 as long as cosine isn't equal to 0, but I don't think we're too concerned with that level of carefulness right now. So another example, look at the two sides. One side is arguably more complicated looking than the other. Grab that thing and write it down. So we have sine x plus cosine x all squared all over the cosine of x. And I need to get it into a position where it looks like the sum of two things, which tells me I'm probably going to want to multiply this out so I can break it into individual fractions. I also want to notice that if I multiply out the numerator, I'm going to get a sine squared plus cosine squared in the numerator, which will equal 1 by the Pythagorean identity. So I'm going to start by just multiplying the numerator out. We'll get sine times sine is sine squared, plus the middle terms, we'll get two middle terms, and the middle terms will be sine times cosine, sine x, cosine x, plus, and then we'll get cosine squared of x. And this is just using the pattern from pre-calc that we learned, where we said, hey, if we have the sum of two things being squared, which we have here, the sum of two things being squared, we know that squaring means multiply that thing, that base, by itself, and you get a times a is a squared, a times b is ab, b times a which is still just AB because multiplication is commutative, at least for algebraic functions and real numbers, plus, and then we get b times b is b squared, so we get that a squared plus 2 of these, 2 ab's plus b squared pattern, and all I did was apply that pattern to the sum. And then I see that I have a sine squared plus cosine squared, which is equal to 1 by the Pythagorean identity. Cosine squared plus sine squared is 1, plus I've got 2 sine x's, cosine x's, and I need the sum of two things, so I might as well break it into individual fractions now because that's where we need to go with this. Break it into 2 fractions. And then we want to recognize that 1 over the cosine is the secant, because cosine and secant are reciprocal functions. And cosine divided by cosine is 1 as long as cosine isn't 0. So we get 2 times sine times 1 is 2 sine x, which is what we needed to show. So here we have another one. We have a ratio of trig functions. The left side's clearly the more complicated looking. Let's transcribe that. Secant x plus tan x times secant x minus tan x. And what we want to recognize with the numerator is that it's a difference of two squares pattern. In other words, if we have a difference of things that are being squared, we know that that factors easily into an AB plus minus form, so we can always go backwards to this form. And that's what I have here. I have an AB plus minus form. It's a difference of two squares, so I can quickly compact it. This compacts to secant squared minus tangent squared using the difference of squares. And now I have a difference of two squares, cosecant of x on the bottom, which tells me I want to look at the Pythagorean identities as potentially being useful. So I'll take that base Pythagorean identity, I'll write it down. I guess we're using x's. And I see that I have a secant, which means I want to do 1 over the cosine squared, which will give me a secant squared. And whatever I do to one side, I have to do to both sides. So I'm going to divide everything by cosine squared, which is going to give me my secant squared. And after a while, you just memorize these. But I think it's good practice deriving them repeatedly until you get them memorized. So sine squared over cosine squared is tangent squared. And then I see if I subtract the tangent squared from both sides, I get 1 equals the secant squared of x minus the tangent squared of x, which is exactly what is showing up in the numerator here. So we can replace that numerator with a 1. And it's 1 over the cosecant of x, and 1 over the cosecant is just the sine because the cosecant and the sine function are reciprocal functions. So here we have one where both sides are somewhat complicated. I'm going to run with this side as being just slightly more complicated to me. So it's subjective. I'm going to start off by saying cotangent of x over secant of x minus cosine of x over sine of x. And I see that I have something here that has a single denominator. It's been written as a single term. So I want to get a common denominator. So I'm going to multiply by secant of x over secant of x. And over here I'm going to multiply by sine x over sine x. And that's going to give me a common denominator, sine x secant x. And my numerator, I have sine times cotangent, sine x times cotangent. But cotangent can be written as cosine x over sine x minus, and our other term is going to be cosine times secant, cosine x times secant. Now if we recognize that cosine and secant are reciprocals, that we could get a 1 immediately. If we don't recognize that, we can write the secant as 1 over the cosine. And then we can do some simplifying. Sine divided by sine is 1. 1 times cosine is cosine x. And we have minus cosine divided by cosine is 1. Cosine x minus 1. And our denominator is the sine of x times the secant. But the secant is just 1 over the cosine. So we have a numerator of cosine x minus 1 over, and now we want to recognize that we have sine over cosine, which is just the tangent function, which is what we needed to show. We needed to show that we could manipulate the left-hand side so that it looked like the right-hand side. So here is our last example. So the left-hand side is the more complicated of the two sides. I'm going to go ahead and rewrite this. Cosine to the 4th power minus sine to the 4th power of x. And I think most instructors expect students to rewrite everything and not just start working from the material that was typed. And what we want to do is recognize that this is actually a difference of squares situation. So in other words, it could be rewritten like this: cosine squared of x squared, and when we raise one exponent to another, we multiply exponents so that we would get our exponent of 4. And we have our minus, and I want to recognize that the sine to the 4th power can be rewritten as sine squared of x, quantity squared, and we would still be over our denominator, which is the cosine squared of x. And if I do this, I can notice, if I notice it's the difference of two squares, I can factor it pretty quickly. It has that AB plus minus pattern where in this case the A is the cosine squared of x and the B is the sine squared of x. And we're put it here, sine squared of x, and it's going to be plus minus. And the reason it's useful is that the cosine squared plus the sine squared is equal to 1 by the Pythagorean identity. So we can replace this with a 1, which is just going to give us the cosine squared of x minus the sine squared of x over the cosine squared of x. And up here I see I have a secant function. So what I'd like to do is get rid of the sine function because secant and cosine are related as reciprocals. So if I'm going to have any hope of getting a secant type of a thing up here, I'm going to need to get rid of the sine function. So the Pythagorean identity is going to be the tool that lets me do that. So I have cosine squared plus sine squared is 1. So if I subtract cosine squared from both sides, I see that the sine squared is equal to 1 minus the cosine squared of x. So I can replace the sine squared in my numerator, cosine squared x, minus the sine squared can be replaced with 1 minus the cosine squared of x. And I'll get this out of my way. This is scratch work, so I shouldn't have it in the flow of the problem. It's a little hard to have scratch paper when you're working off the computer screen. So if and I don't want to lose my denominator because that would be dumb of me. We have a cosine squared of x sitting here. So if I distribute this minus into the parentheses, I'm going to get minus is plus. So I'm going to get cosine plus cosine is 2 cosines squared of x, and then minus a 1, and it's going to be over the cosine squared. So I'm going to break this up into two pieces because up here I have 1, two pieces, so I'm going to put each thing over the common denominator. Cosine squared of x, and cosine squared divided by cosine squared is 1, so 2 times 1 is 2, minus 1 over the cosine is the secant, so 1 over the cosine squared is the secant squared of x, which is what we needed to show.